In this video, we discuss about the Zener diode, that is a special diode made up of the semiconductor. So this Zener diode is actually constructed using the desired doping percentage in the PN junction diode. It is similar to the semiconductor diode, but the doping percentage is different from that of the semiconductor diode. So when crystal diode or semiconductor diode is reverse biased, it is observed that at a breakdown voltage, the reverse current increases sharply or suddenly, and that will going to damage the diode. Okay, in semiconductor diode, when it is reverse biased, there will be the phenomena of thermal runaway because of the flow of very high current when once the breakdown voltage is reached. This breakdown voltage in a semiconductor diode depends on the amount of doping. The doping can be used to control the breakdown voltage. If the diode is heavily doped, the depletion layer will be very thin, and consequently the breakdown of voltage of the junction will occur at lower reverse voltage. At the lower breakdown voltage, you can observe the sudden increase of current if the diode is having higher doping percentage. On the other hand, a lightly doped diode will have the higher breakdown voltage. So that is how we can control the breakdown voltage based on the doping. When ordinary crystal diode is properly doped, so that it will show very sharp breakdown voltage, and that diode is called as the Zener diode. Okay, so properly doped diode, which is designed so that it will have a desired breakdown voltage and there will be sharp increase in the current, and that kind of diode is called as Zener diode. So what is the definition of Zener diode? A properly doped crystal diode which has a sharp breakdown voltage. It is called as Zener diode. Okay. So these are the very important properties or characteristics of the Zener diode. So one of the properties that a Zener diode is just like an ordinary diode, but it is properly doped so that it will have very sharp breakdown voltage. There will be sudden increase in the current at breakdown voltage. This Zener diode is always useful, or that is going to work properly when it is reverse connected. That is, Zener diode is having useful applications in the reverse biased condition. Okay, when it is forward biased, it will have the same characteristics as that of the ordinary diode. So this Zener diode has a sharp breakdown voltage, and we call that voltage as Zener voltage. In ordinary diode, that sharp increase in current is called as breakdown. So here, the voltage at which there is a sharp increase in the current when it is reverse biased is called as Zener voltage, and we represent it by Vz. So when it is forward biased, already I have told you, it will have same characteristics as that of the ordinary diode. So this is the circuit symbol of the Zener diode. So it is having same circuit symbol except that there is a Z symbol on the N-type region of the semiconductor p-n junction. So this is P region, this is N region, and this mark indicates that this diode is the Zener diode. So basically, normal ordinary semiconductor diode has a vertical line at this position on the N side junction or n-type semiconductor in a p-n junction. Z symbol is used to represent the Zener diode. This is the circuit symbol of the Zener diode. So what is the VI characteristic of Zener diode when it is forward biased and when it is reverse biased? It is having the same characteristic as that of the ordinary diode when it is forward biased. So this first quadrant graph shows you the forward biased Zener diode characteristic. So when forward voltage is increased, then there will be increase in the current, and that is having the linear increase. So some not linear, non-linear increase. Okay. So here the resistance of the Zener diode will be very small, and it will conduct the electricity even at very low voltage. Okay. So if you consider the reverse biased condition, that will have the different kind of characteristic. Basically, the normal semiconductor diode has the increase in current at very large voltage, but here At a small voltage also, there is a sudden increase in the current, but there is no the phenomena of thermal runaway. The diode will not get damaged even when this breakdown voltage is reached in a Zener diode. So this voltage at which there is a sharp increase in the current is called as the Zener voltage. And here, even though if you increase the voltage beyond this VZ, there will not be any change in the voltage across the Zener diode, but there is a increase in the current. Okay, so there is an increase in the current when the voltage across the Zener diode reaches VZ, but there is no change in the voltage, or a very small change in voltage also going to increase the current without any change in the voltage. So that is the reason why the resistance of the Zener diode becomes almost zero, okay, when it is reverse biased. When it reaches the voltage VZ, the voltage across the Zener diode remains constant when it reaches the value of Zener voltage. When it reaches the value Vz, after that, the voltage will not change at all. So that means the voltage across the Zener diode remains constant, even though there is a increase in the current. So this property is very useful in the voltage regulation. You can get the constant voltage across the Zener diode once the reverse biased voltage of the Zener diode reaches the Zener voltage Vz. So this property is useful in the application of voltage regulator. That is the reason why Zener diode is usually used as a voltage regulator. So what is the equivalent circuit of the Zener diode? What happens when it is forward biased and what happens when it is reverse biased? Usually the reverse biased Zener diode has the valid applications. So let us consider two conditions. If V is greater than or equal to Vz, suppose the applied reverse voltage, that means positive of the battery is connected to N region, negative of the battery is connected to P region of the Zener diode. That means the applied voltage is, if it is greater than the Zener voltage, then what will happen? Then there will be flow of current in this direction, and that is called as the Zener current Iz. Okay, so that means there is a sudden increase in the current and the voltage across the Zener diode remains constant at Vz, even though if you increase the input voltage. So we call that state as on state. So in this state, the current increases very sharply when it is reverse biased, when applied voltage is greater than Vz. Okay, then the current increases very sharply. The voltage across the Zener diode is constant at Vz, even though the current through it changes. Even though the current increases, the voltage across the Zener diode remains constant at Vz because there is no change in the voltage of the Zener diode. Therefore, in the breakdown region, an ideal Zener diode can be represented by a battery of voltage Vz as shown in the figure. Okay, since voltage across the Zener diode remains constant, that is the reason why Zener diode just acts like a constant voltage source that is having the voltage Vz. So this is the equivalent circuit of the Zener diode when the applied voltage V is greater than Vz, and we say that the Zener diode is in on state. Under such condition, the Zener diode is said to be in the on state. That means it conducts the current. Very high current will flow through it, or sufficiently high current will flow through it, but voltage remains constant. On the other hand, if applied input voltage is less than Vz, when Zener diode is reverse biased, but voltage is greater than 0 volt, then the Zener diode will be remain in off state. Under such conditions, the current will not flow through the Zener diode because the current will start to flow through the Zener diode once the breakdown voltage or Zener voltage is reached. Suppose the applied voltage is less than Zener voltage, there is no current in the Zener diode. So that will just act like a open circuit. The Zener diode just acts like an open circuit so that the current through the Zener diode remains zero. So we say that this is the off state. Off state means there is no flow of current. On state means there is a flow of current. So these are the two states of Zener diode identified based on the applied reverse biased voltage. If reverse biased voltage is greater than Vz, Zener diode will be in on state with constant voltage. When the applied voltage is less than Vz, the Zener diode will be in off state, that is the open circuit state. So this property is used for the application of the voltage regulator. Let us take that. Zener diode as a voltage regulator. So this circuit shows the Zener diode used as a voltage regulator. So here, irrespective of the input and irrespective of the load, we should get the constant output voltage. And that circuit is called as voltage regulator. Voltage regulator means the circuit which gives you the constant output voltage irrespective of the input voltage and the load resistance. So this circuit consists of the input voltage EI connected with a series resistance R, and the Zener diode is connected in a reverse biased condition, and parallel to this Zener diode, the load resistance is connected, so that the voltage across the Zener diode will be always equal to the voltage across the load because they are in parallel. The parallel circuit components will have same voltage across them. Okay, so this circuit can be analyzed by taking the various currents flowing in the circuit. So here IZ is the current flowing through the circuit. Okay, here what happens? Once the input voltage reaches the Zener voltage Vz, the voltage across the Zener diode remains constant at Vz. That will not increase at all. Same voltage will appear across the load resistance, so that this output voltage will be exactly equal to Vz. So that is going to be constant. Okay, so that is how the Zener diode gives you the constant output voltage even though there is a change in the input voltage. So what happens? If input voltage is increased, there will be higher voltage drop at this series resistance, so that voltage across the Zener diode remains constant. Okay, whatever the extra voltage given, that will drop across the series resistance, so that Vz will be constant. Suppose load resistance is varied. Suppose load resistance increases, then what happens? The current through the load decreases, then automatically the current through the Zener diode automatically increases, but there is no change in the voltage. Okay, even though the current increases, there is no change in the voltage. Okay, that is how the voltage across the load remains constant, even though you change the input voltage, even though you change the output resistance or load resistance RL. Okay, so let us take the two conditions or how to analyze this Zener diode circuit as a voltage regulator. Let us take the same circuit. Suppose let us take the input voltage is less than Vz. What will happen? This Zener diode will be in off state. The entire current will flow through the load, or this output voltage will be equal to the input voltage minus the voltage drop across this resistance. Okay, so that the output voltage will not remain constant when the Zener diode is in the off state. Once the Zener diode start to conduct the electricity when it is in the on state. Okay, this is circuit showing the Zener diode in the on state when input voltage is greater than or equal to Vz. Then the current will start to flow through the Zener diode, but voltage across the diode remains constant. Same voltage will appear across the load resistance, so that the output voltage E naught will be equal to Vz. Okay, let us take that mathematical expressions to understand this Zener diode as a voltage regulator. Two states will consider the off state of the Zener diode. That is when the Zener diode is not conducting the current. That is the case where the input voltage is less than Vz. When the Zener diode is not conducting the current, it means the Zener current Iz will be equal to 0 because Zener diode is in open circuit condition. Therefore, the total current I will be is equal to IL. I have not shown here. This is the total current I, and that will be equal to the load current IL. Okay. Now the voltage drop across R. What is the voltage drop across this series resistance? That will be equal to the input voltage minus the output voltage E naught, because this R and RL will be in series. So the applied voltage will divide into two parts, that is voltage drop across R and voltage drop across the RL. Therefore, the voltage drop across the series resistance R will be is equal to input voltage minus output voltage, that is EI minus E naught. Therefore, the output voltage will be E naught will be is equal to EI minus VR. Input voltage minus the voltage drop across the resistance. And also, if load current is IL, then output voltage can be given by E naught is equal to IN into RL. That is in accordance with the Ohm's law. Current into resistance. The voltage will be is equal to current into resistance. Okay. So this is how we can calculate the output voltage that depends on the load current and the load resistance. Okay. Whereas this load current is equal to the total current. Okay. So that the total current can be calculated by taking this VR divided by the input voltage will give you the total current. That is how you can analyze this circuit. Suppose in the on-state condition of the Zener diode is considered, then the Zener diode will conduct the current IZ and there will be total current I here. Then current through the load resistance is taken to be IL. Okay. Then the output voltage, this E naught will be is equal to the Zener diode voltage VZ. So that is going to be constant. So voltage will be regulated here. Similarly, you can calculate this output voltage as a product of the current into resistance, that is IL into RL, the load current into the resistance, load resistance. Now, if you apply the KCL at this node, then the total current will divide into two parts. The total current I will divide into IZ and IL. That is current through Zener diode plus current through this load. So I will be is equal to IZ plus IL. So what is IL here? What is the current through the load? That is given by this Ohm's law, output voltage E naught by the load resistance RL. What is E naught here? E naught is the Zener voltage VZ. And also you can calculate the total current I, that is equal to the input voltage minus the output voltage divided by the series resistance. Again, you can substitute E naught is equal to VZ here. So that will be input voltage minus VZ divided by the series resistance R. So we'll get the expression for load current as E naught by RL, expression for total current as EI minus E naught by R. So we can calculate what is the Zener current IZ using these three expressions. So IZ will be total current minus load current. IZ will be total current minus load current. From this expression, you can get substitute for I and substitute for IL. You will get the Zener current is equal to EI minus E naught divided by R minus the load current E naught by RL. That is how you can calculate the output voltage, load current, and Zener current. These are the three parameters used for the analysis of the Zener diode as a voltage regulator. So these expressions are very important. So just to remember, the output voltage will be VZ, that is constant. And output voltage can also be represented by current into resistance. Then total current will be divided into two parts, that is IZ along Zener diode, IL along the load resistance. Okay. Then you can get the expression for load current as output voltage by load resistance, and total current can be represented by this expression. Okay. And you can calculate the value of Zener current that will be depending on this E naught, EI and R. Okay. So what happens here? If input voltage is varied, so this output voltage remains constant, then this total current is going to change. Okay. So what happens? If input voltage is varied, then the output current will remain constant. The extra voltage will drop across R and extra current will flow through Zener diode. If external load is changed, if load is increased, then the voltage across the load remains constant. Okay, so that there will be corresponding decrease in the current, so that the IL into RL, that product remains constant. Whatever the extra current that will flow through the Zener diode. Okay, so that is how the output voltage across the load remains constant, even though if you change the input voltage and the output load resistance. That is how the Zener diode will give you constant output voltage, and it is called as voltage regulator. Okay, so this is about the Zener diode and application of Zener diode as a voltage regulator.